Okay, so here we've got an integral equation. Ux is equal to e to the x minus 1 plus the integral of t ut dt with limits from 0 to 1. Basically, equation is of this form where we see the limits are constants. So we're looking at the Fredholm equation, integral equation. So what we have is fx, which is e to the x minus 1. And also we've got lambda over here, which is 1. And we have the kernel, k x comma t, and that kernel is equal to t over here, which is this. Right, so we're going to be using the Adomian decomposition method to solve this integral equation. So I'm going to say u naught x, which is e to the x minus 1. And from here, we can find u1 of x. So basically what we do, we take this part of the integral equation where we've got lambda, all right, and lambda, which is basically 1. So I've got a, b, and k of x comma t u naught of t dt. So the x is going to be substituted for t. So if I do that, we know that this lambda is 1, so we don't have to worry too much about it. Got 0, 1, and then this is t basically, which is this, and then u naught of t, we found it was e to the x minus t. Because we're substituting x for t, so this becomes then e to the t minus 1 dt. So now we're going to have to integrate this. So we distribute the t inside, so t e to the t minus t dt. So over here I'm going to be using the integration by part, and if we do that, we're going to get integral of t e to the dt minus integral. First of all, I'm going to split the integral in two, sorry about that. So t dt 0, 1, those are the limits, and from here now we can just use integration by parts. Integration by parts. And for this, using integration by parts, we're going to get u is equal to t, and then dv is equal to e to the t, therefore v is equal to e to the t. uv is t times e to the t, so t times e to the t, and immediately we can apply the limits. 0, 1 minus the integral of v dt, and v is e to the t, and dt is as it is dt. And from there, we're going to minus, okay, the integral of this one here, which becomes then t square over 2, limits going from 0 to 1. And if we were to simplify this further, you just substitute your limits here, you're going to end up with 1 times e to the 1. So that becomes e to the 1, which is e, and then e to the 0, okay, which is basically 1, and then t is 0, 0 times 0 times 1 is 0, so I end up with e. Basically now minus, okay, e to the t, this is the upper limit minus the lower limit, so the integral here is e to the t, and so that becomes e to the t. If you integrate this, you sure get e to the t, and e to the t limits from 0 to 1 again, minus over here, if you were to apply the limits, you're going to end up with half. So what we have is e, and then minus, in brackets, e to the 1 minus e to the 0, so which is e minus e to the 0, and then minus the half. And Simplifying further, e minus e cancels out, and I've got 1 minus minus becomes plus, e to the 0 is 1. So I've got 1 minus the half. So basically now I've got half. So that means u1 of x is equal to half. Remember, we're trying to find this, okay? So u1 of x is half. So now we can go to u2 of x, decomposing further, which is, again, we know this is lambda, and then a, b, kernel, x, comma, t, u1 to the t dt. All right, so what we're saying is that this is now u2x, okay, is equal to 0, 1, take that integral again, this part here, and instead of u1 now we're going to have u1 is already used, so we had u0 to get u1, so now u1 to get u2. So what we have is then t into u to the t and u to the t, which is u to the x here, and that was half. So we get half times t, which is half t. So half t dt, all right? And if you were to integrate this, you're going to get t squared over 4. So I'm going to just want to put this into the camera further so you can see it clearly. And well, that's going to be t squared over 4, applying the limits from 0 to 1. You're bound to get 1 to the square over 4 minus 0 ends up as 1 over 4, which is basically 1 over 2 square. Sorry. So now if we were to go for u3, you will see a pattern is going to be emerging, and I'm going to get 1 over 2 to the cube. And this is going to go on forever like this. So u4 will then be, u4x, 1 over 2 to the power of 4. So basically now, what are we saying is that we have a pattern that follows, and the pattern is such that, but then again, so let's see, so all of that could equal to, so 1 over 2 to the cube, all right, blah, 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 and so on. I can say u to the n, un, and this is 1 over 2 to the power of n. Because the more you move, the next term is the power, add 1 to it, 3, 4, 5, 6, 7. So we've got, then again, u3 is 2 to the 3. u2 is 2 to the power 2. So therefore, basically, un is 2 to the n. So 1 over 2 to the n. And from here, we also know that ux is equal to u naught of x plus u1 of x plus u2 of x plus and so on. And from here, we can see that we've got then ux is equal to e to the x minus 1, what we had at the beginning from the integral itself, okay, plus, then we got the first one, which is half, okay, plus 1 over 2 to the square, plus 1 over 2 to the cube, plus, and so on. So all of that's going to be equal to e to the x minus 1 plus, this looks like a geometric pattern. So I can factorize the half outside, and inside I'm left with 1, because 1 times half is again half, all right, plus half, okay, plus 1/4, plus, and so on. Right, so, because 1 times half is half, 1 half times 1 half is 1 over 2 to the power of 2, 1/4 times 1 half is 1 over 8, and 1 over 8 is 1 over 2 power 3. So let us continue further. So that looks like to me like the sum of sum of all of that is geometric progression. So from this sum of geometric progression, we have then ux is equal to e to the x minus 1. Then we plus the half times the sum of this geometric progression. So, and from this sum of geometric progression, it could be observed that this is going to go on forever. Right, so if this goes on forever, we're looking at this sum to infinity. We know that the sum to infinity is a over 1 minus r, where the modulus of r is less than 1. And from here we've got a as 1, r is basically half, and so we're just going to apply this and find the sum to infinity. So the sum to infinity is equal to the first term, a over 1 minus r, 1 minus half, so that's 1 over half, which is then 2. So basically now what I have is that ux, my final result, is going to be equal to e to the x minus 1 okay, plus half into the sum to infinity is basically 2, so half multiplied by 2. So this comes to e to the x minus 1. Half times 2 is plus 1. The plus and the minus cancels out, and I got u to the x is equal to e to the x. So that's the final answer for this Fredholm integral equation. I hope you've enjoyed this video. Please don't forget to like and subscribe. Take care. So this was the Adomian decomposition method.